Okay, it's time. Let's start. Good morning. Now we got to do better. Good morning. Much better. Thank you. Okay, so we're going to be looking at section 3.5. The topic is implicit differentiation. Now, if you got a chain rule, then this part just follows very naturally. Everything we're doing here in this section is entirely based on chain rule. So before we look at that, let's talk about what it means to have something to be in the implicit form. We can write all functions in either the explicit form or implicit form. Explicit means you know exactly how that function depends on a variable. So here's an example of an explicit function. Y is equal to x squared minus 5x plus 10. You explicitly know what y is equal to once you determine what x is going to be. You know the relationship between y and x directly. And you know, once you determine what x is going to be, you know what y is going to be. So the feature for this kind of form is you have y on its own side. And it can only appear once. Compare that to the implicit form. Okay, so here's an example of an implicit form. It's an equation of a circle, right? Y is not on its own side, and it shows up, even though it shows up once, it shows up in an inconvenient form, y squared. Here's another example. Here we have y showing up more than once, and again, showing up in an inconvenient form in some way. The problem here is once you determine what x is going to be, you decide what x is going to be, there's usually more to do before you can find out y is equal to. If I want x to be 1, for example, I got to subtract that and take the square root. If I want x to be 2 here, there's a little bit more to do before I can find out what y is equal to. Some of these can be expressed in either form, like the square equation, a circle equation, for example. Notice that this one could also be written as y is equal to plus or minus square root of 9 minus x squared. So I turn it from an implicit form to an explicit form. But not all of these things can be done. For example, if you look at this one right here, you're going to have a hard time solving for y so that it only shows up on one side. You can divide it by x, but you still have that sign of y here. You can take the inverse sign, but then you still have a y dangling around here. There's a lot to do before you could achieve what you want to have y in the explicit form. Okay, the thing about explicit form is if you have the equation in explicit form, finding the derivative is very easy. You know all the rules there's to know. You know the product rule, quotient rule, chain rule, the basic rule stuff. But in implicit form, like this one right here, for example, if I can't write y is equal to something, then knowing the basic rules I know, there's not a way to find the derivative very, very easily and cleanly. Okay, so that's where implicit differentiation comes in. If I have things in the implicit form, the technique allows me to find the derivative of y. Okay, let's see how that works. And we'll do this by example. So let's say we got an equation, a function y defined implicitly this way. X cubed plus y cubed is equal to 8. Now you notice that this one is something we could actually turn into an explicit form if we wanted to. But suppose we couldn't do that. Let's just leave it implicitly defined, and let's find out how to find the derivative of y. Okay, the start is very simple. Just go ahead and take derivative on both sides. With respect to x, x is the independent variable here. If both sides are equal, then derivatives must also be equal. So we get derivative of the left side equal the derivative of the right side. The left side could be further split. The right side is not a problem. We know how to handle that. It's an 8, so derivative is 0. So we don't have to worry about that. Okay, now here's the key step. You have to remember that y is a function of x. So y is really something to do with x. We don't know what it looks like necessarily, but we know it has to be something that depends on x. So that means in this part right here, when you take the derivative of y cubed, it's really no different than taking the derivative of u cubed when you use the chain rule. When we do the chain rule, remember we let u be something that depends on x. And that's precisely what's going on here. This y here, we don't know what it looks like, but we know it's something that depends on x. So derivative of that is really the same as derivative of u cubed. And so what's going to happen here, this part is easy. Derivative of x cubed is 3x squared. And derivative of y cubed here, think of it as u cubed. Remember, you bring the power down. You keep that base the same. Reduce the power by 1. And then you have to account for the fact that this u and this y here is something more than just an x. So that's where we have to insert this extra dy dx. Right-hand side, 0, of course. Okay, does that make sense to everyone, where this dy dx came from? Yes? No? Nod your head if yes, so I can see. Good, good. Okay, so remember, it's a chain rule going on here, right? This thing depends on x, derivative of something complicated with respect to x, cubed, bring the power down, keep that, reduce power, dy dx. Okay, now go back to the original question. We want to know what dy dx is equal to. From here, we can find it. Just do simple algebra. We get 3y squared dy dx equal to negative 3x squared. So dy dx must be equal to negative x squared over y squared. Okay? Notice that this derivative is also implicitly defined. And that's very often the case. If you start with an implicit function, the derivative will also be in the implicit form. You could turn that into explicit in some cases, but it's not always going to be doable. Okay, so we got the derivative implicitly this way. Take a look at this function again. Remember, we said earlier that this is something that we could also rewrite in the explicit form. So let's try rewriting this in explicit form, and then take the derivative. See if it matches what we got here. Again, it's not always doable, but because we can do it for this one here, let's just see what happens. We start with that. So very, very easily, we rewrote it this way. Y is equal to 8 minus x cubed, and then cube root of that. Now we know finding the derivative is not hard. Just use the chain rule. Bring the power down. Keep that base the same. Reduce the power by 1. And now we multiply by derivative of this to account for the fact that it's more than just an x. So we get 0 minus 3x squared. Okay, rewrite it. The 3 and the 1/3 go away. Let me put a negative x squared on the top. And downstairs, we have 8 minus x cubed to the positive 2 over 3. Compare this to what we got on the last page. They should be the same thing. They look different, but they should be. It's very easy to see that they are indeed the same thing. Because notice we can rewrite the denominator just a little bit. I can rewrite 8 minus x cubed to the power of 2 over 3 as 8 minus x cubed to the power of 1/3. Then square that. And by doing that, you notice that this stuff in the brackets, that's precisely what we call y in the first place. So downstairs is really just y squared. So they match, as they should. Right? So that's our y. Okay, this is not always doable because not all functions can be turned into explicit all the time. So we're not going to be able to do this all the time. In general, even if you could, it's not always something that you want to bother doing anyway. But for the purpose of learning implicit differentiation, it's good to see that they are indeed the same thing. Questions? Okay, let's do more examples. Try this one. One over x plus 1 over y is equal to 2. Okay, it's implicitly defined. Y is not on its own side, and y doesn't show up in a convenient way. But it doesn't matter. Let's just rewrite it. That's a plus. I'm making it worse. That's a plus. So that's x to the minus 1 plus y to the minus 1 is equal to 2. Just like in the last one, we differentiate both sides. And once again, the key step is to remember y is a function of x. Okay, so when you take the derivative of y to the minus 1, you got to remember the chain rule applies. First part is simple, negative x to the minus 2. And now for y to the minus 1, bring the power down, minus 1 times y to the minus 2. And then because of the chain rule, y is some function of x. It's like u to the minus 1. Y minus 1 comes down, reduce the power by 1. Multiply by derivative of that, dy dx. So essentially, every time you differentiate something involving y, be prepared to include this part as a consequence of the chain rule. Right-hand side is 0. It's a constant. Okay, now this is pretty easy. We get minus y to the minus 2 dy dx equal to positive x to the minus 2. So dy dx is equal to negative x to the minus 2 over y to the minus 2, or negative y squared over x squared. Okay, does that make sense? Any question on this one? Okay, now let's look at this next one. This next one, we got a little bit of complication going on with one of the parts. X squared plus xy minus y squared is equal to 4. And this one is something that you truly cannot rewrite in the explicit form. We got y showing up twice. And try factoring y out to put on its own side. You find out that this simply cannot be done, at least easily. Okay, so let's do implicit differentiation again. We take the derivative on both sides. First part is easy, 2x. Now the middle part, this is where things get a little bit tricky here. Remember, y depends on x, so y really is a function involving x. So what's going on here is x times another function of x. This is a product of two functions of x. That y really is some function involving x. If we know exactly what it looks like, then we wouldn't be doing this. We don't know what it looks like, but we still know fundamentally it's some function of x. So that means when I take the derivative here, I have a product of two functions involving x. I must use the product rule. So we get, here we go, first times the derivative of the second. First times the derivative of the second. What's the derivative of y? dy dx. Yeah, exactly. We don't know what it is, but we know its derivative by definition is dy dx. Right? Plus the second times derivative of the first. First is x, derivative is 1. All right, so this is the part where we got from the product rule. Any question on that part? Okay, good. Next one, what do we get here when I take the derivative? 2y dy dx. Good. Gotta remember, chain rule, right? Y is something to do with x. This is blah squared. Derivative of blah squared is 2 blah to the first, d blah. Same thing, just like the chain rule. Exactly the same as chain rule. That's a 4 here. I'm sorry, jumping ahead here. But it's a 0 anyway. So, right-hand side derivative of a constant, whatever it happens to be, is at 0. Okay, so if you keep in mind that every time you take derivative of anything to do with y, you have to include this thing from chain rule. Now let's solve for that. Let's see, we got these two things involving dy dx. Let's keep them on the left side. Everything else without dy dx I'll put on the right. So minus 2x minus y. Let's factor out dy dx on the left. And then divide that. And there we go. Okay, if this were x over y, then you would be using the quotient rule. And again, you got to keep in mind, every time in any part of differentiation involving y, you have to tag on dy dx. Any question on this example? All right, good. Okay, if you think you got that, try this one on your own. I'll give you 2 minutes. Okay, find what y prime is equal to if the function is defined implicitly as y sine x is equal to x sine y. 2 minutes. All right, that's 2. Okay, so let's take a look at what we should get. First step, very simple. Simply take the derivative on both sides. And now we got to recognize that on both sides here we have product of two things involving x. This y really is some complicated thing involving x. So that's some function of x times another function of x. That's a product rule here. Same thing here. X times something else that involves x. So we got to use the product rule on both sides. Left side, first times the derivative of the second cosine, right? Plus the second times the derivative of the first. We don't know what y looks like, so derivative by definition is y prime. Right-hand side, first times the derivative of the second cosine of y and y prime, right? Remember, this is sine of something involving x. By the chain rule, derivative is cosine of the same thing times the derivative of that thing. First derivative of the second plus the second times derivative of the first, and that's just a 1. Okay? Now what's left here is not very hard. Just find out what y prime is equal to. Bring everything that's got y prime in it to the left or to the right. It doesn't matter. So let's bring this guy over. We'll move this to the right. We want y prime, so let's factor that out on the left. Right-hand side, there's nothing more to do. Keep it the same. And now we can find out y prime. And there we go. Okay, how many of you got this? All right, that's good, good, wonderful, wonderful. Very happy to see. If you didn't get it, make sure you find out where you went wrong. I'm guessing you probably left out one of these y primes. That's a very common mistake. Any question on this example? Yeah. You could put on the right if you want. The goal is to find out what it is equal to. So bring everything to one side and somehow isolate it. Other questions? Yeah. Here? No, it doesn't. That's a good thing here. Good thing to point out. It does not go into the cosine. This is cosine of y times some other quantity. So it's cosine of y, that's one thing, right? Times this some other thing. It is not the same as cosine of y times y prime. If you look at where this thing came from, this is the derivative of sine of y. Derivative is cosine of y separately times derivative of y. So they're not, you cannot merge the two. Same thing here. These two guys cannot be merged. Good, good. Other questions? Okay, let's take a look at inverse trig functions. Let's find out what their derivatives are. Let's start with the inverse sine. if y is the inverse sine of x, what is y prime equal to? And what we can do is actually use implicit differentiation to find out the derivative of y prime. Okay, and here's how you can get it. We can rewrite y is equal to inverse sine of x as sine of y equal to x. We're still asking for y prime. Okay, now if you look at this thing here, this is really no different than what we have been doing. We have something implicitly defined. We start by taking the derivative on both sides as usual. Remember, every time you differentiate anything involving y, you got to remember that y prime needs to be applied, needs to be multiplied in. Derivative on the left, sine of y is cosine of y times y prime, right? Right-hand side derivative of x is 1. So we see that y prime is equal to 1 over cosine of y. Okay, so we got the derivative, but we can do better. We can actually get rid of y. Notice that because we started out with an explicit function, it would be great if you can leave the derivative also in an explicit form. That's explicit. This is implicit. Not very good, not very useful. So we got to find a way to get rid of y. So here's the thing. We have sine of y is equal to x. So we can relate sine of y to x in some way. We have a cosine of y that we don't want. But we know sine and cosine are related in some way. So if I can relate this to that, then I can eventually relate that to x. And how do you relate cosine and sine? We have one identity that can do that for us. The Pythagorean identity, right? So we know cosine squared of anything plus sine squared of anything is equal to 1. We normally see these as x, but as long as they're the same thing, that identity stays true. So now check this out. This thing right here, this is sine of y, the whole thing squared. But sine of y really is x, right? So this is really x squared. So what I'm seeing here is cosine of y, the whole thing squared, plus x squared is equal to 1. I don't want cosine of y in here, so that's easy. Okay, so I subtract x squared from both sides and I take the square root. Now I can take this entire thing here, replace that, and finally I see that y prime is equal to 1 over radical 1 minus x squared. In other words, the derivative of inverse sine of x is 1 over radical 1 minus x squared. Okay, does that make sense? And the good thing about this is that if you know the basic rule, remember, the basic rule is still going to be true even when we change this to something other than x. So chain rule says that a more general formula there. Remember, all the basic rules can be kept the same with a minor modification. If I change that x to anything other than x, then the derivative of inverse sine of u is still 1 over radical 1 minus u squared times du dx to account for the fact that a u is more than just an x. Any question on this? Okay, I do have a question for you actually. Look at this thing right here. How come when I took the square root, I only included a positive radical? What happened to the negative radical there? Because what? It can be negative. It actually can. So what's wrong with the negative radical, negative root of this thing? Why? Domain of what? You're on the right track, but let's be more precise here. Here's the clue here. Look at this thing. What's the range of inverse sine? Negative pi over 2 to positive pi over 2. So that's the fourth and the first quadrants, right? So what's cosine in the fourth or the first? Positive. That's why we didn't include a negative root here. Two. So quadrant 4 and quadrant 1. Cosine positive. All right, you're on the right track with the domain and range kind of thing. Now, if you do the same thing with inverse cosine and inverse tangent, you'll find out this thing here. The inverse cosine has a derivative that's equal to minus 1 over radical 1 minus x squared. So it looks very much like the sine one, except the sign is different on the top. And of course, if you know the basic rule, then chain rule doesn't change much. And then for tangent, inverse tangent, we get 1 over 1 plus x squared. And once again, if you know the basic rule, you know the chain rule. Okay, I don't recommend memorizing these because if you need them, first of all, you don't need these too much. It's not very often that you encounter inverse sine, cosine, and tangent in most applications. It's not very common. The only time you really need it is on exam 2. So I don't recommend memorizing them, but if you remember how to get it, then whenever you need it, just rederive it. It doesn't take that much time. If you choose to memorize, that's fine. But like I said, I would recommend not to memorize them. Just know how to get them. Let's do one example here. Let's say the function is inverse tangent of 6e to the x. Yeah, good enough. Okay, there are a couple of things you can do. You can simply use the formula if you want to. Or you can do, so I'll write down the options. You can use the formula above, or you can simply use implicit differentiation. Since this section is on implicit differentiation, I'll show you how to do it that way. Rewrite it as tangent of y is equal to 6e to the x. Take the derivative on both sides. Derivative of tangent of y is secant squared of y. And now the all-important y prime. Chain rule again. Right-hand side is simply 6e to the x. Okay, so then we get y prime is equal to 6e to the x over secant squared of y. And now we use the identity, one of the identities, to get rid of y. Remember, if you know just this one here, you can always divide by sine or cosine as needed to get the other ones you need. Okay, so let's divide by cosine squared because I want secant to show up. I want the secant to show up somewhere. And I know 1 over cosine is secant. So I get 1 plus tangent squared of y is equal to 1 over cosine, that's secant, squared, squared. Okay, second line from the bottom of last page. Remember, we had tangent of y is equal to 6e to the x. Second line from the bottom on the last page. So that means 1 plus 6e to the x squared is equal to secant squared, secant y squared. All right, so we don't want that. Now we know exactly what it is in terms of x. So this guy down here, bring it down, it's going to be 6e to the x over, not this anymore, but this. And that can be written as 6 squared is 36. E to the x squared is e to the 2x. And there we go. All right, so that's how you handle inverse trig. Same thing with inverse secant, inverse cosecant, and all that stuff. We rarely use those things. Tangent, cosine, and sine are the most common ones. Even then, it's pretty rare. Okay, that's it for today. See you Wednesday.
Yeah, I know. So I took the liberty of printing out getting it from my advisor. I got it signed by my old,
Okay.
and they told me that you need your signature here. And if you're all right with me joining the class. And I don't really know if it's W or WF because I don't know what that is. But I could ask a hobby if you don't know.
It's normally W, but I think because you're switching to the same course, it
Yeah.
actually doesn't matter.
Okay.
We'll let
Yeah.
Hobby figure it out.
I can fill out the rest then.
Okay, great.
Thank you very much. I'll see you Wednesday.
Professor Chekhov. I had a question about at one point you found it was between negative pi over 2 and pi over 2. How did you know that?
That's from take a look in three places. So 3 lessons ago, when we were dealing with the inverse trig functions, remember we sine by itself is not one to one, so it doesn't have an inverse. Remember we cut off sine from minus pi over 2 to positive pi over 2 to retain it one to one.
Yeah.
This is a one to one part. So from that, that gave us the
I don't know what you're asking. My
sine
question
at
more.
inverse sine at minus
Just
pi
letting
over
it.
2 positive pi over 2.
Got it. Excuse me. Hi, nice to see you again. I have a question about your method here. So I don't know if this is a coincidence or not, or if you can do this all the time. So cosine of y, you can rewrite y as sine inverse of x. So you can rewrite it as 1 over cosine of sine inverse of x. So you can use like
Yeah, yeah,
trig
that's
to
fine
do that.
too.
Does that always work?
Yes, because this and that, this is a triangle. So using this or using triangle, we're doing the same thing.
Okay. Thank you. Excuse me.
Yeah.
I know your office hours are at Wiley, but specifically, where are your office hours at? On the thing it said, okay. Sorry. So, math building,
Yep.
what time?
9 a.m. to Friday, 9 to 11.
What time?
9 to 11. 9 a.m. to 11.
Oh, so basically now.